the second night of the AP Chem Cram preview. I'm so excited for you guys to be here. My name is Steven. I'm part of the Fiveable team. And we're really excited to get started. You know, we are fully in it. Cram season is upon us. This week is really exciting for us. We got the chemistry Cram preview happening tonight, and then on Wednesday the Cram finale starts for real. Super exciting. So really excited. If you joined us last week, welcome back. If you're brand new here, if this is your first time with the chemistry squad, welcome. So really quick before we get rocking, I am going to pass it over. We have a really short video that our founder Amanda recorded, and we're going to watch that really quick.
I'm super stoked to be here for another Cram preview. You know, if you can hear me, you can see me, let us know in the chat where you're coming from. We'd love to see just like how many students from around the world we have coming together, all here for the same reason, to review AP Chemistry. So my name is Amanda Duemerol. I am the founder and CEO of Fiveable. I've been helping students feel confident for their AP exams, well, really for like 10 years, which is kind of wild, but I've been doing Fiveable for 5 years, and we're in Cram season. This is like my favorite time of year. It's like Super Bowl time. I know that you are probably feeling pretty stressed out, but that's why we do these, because I want you to feel calm, cool, collected, ready to go. So tonight, our amazing student hosts who have already taken AP Chem, they were you some time ago. They know exactly what you're going through. They're going to be reviewing equilibrium tonight. I wish I had some nice chemistry joke, so y'all can make chem jokes in the chat all night long. But that's going to happen tonight. So we're doing this another free Cram preview. And with that, we're only a few days away from the actual Cram finales for Chem. So your test is coming up quick. I hate to stress you out even more, but it's like right around the corner. So on Wednesday night is the very first Cram finale for Chem. Actually, you're the first Cram finale that we're running for any subject. So Wednesday, Thursday, Friday, Saturday, and Sunday night, 5 nights in a row, 3 hours each. We're going to be reviewing literally everything. So we're going to run through all the units. We're going to run through FRQs, multiple choice. We have our students putting together even just like misconceptions about chem and like how it should be organized. And all this stuff is going to make it so that when you wake up on Monday and it's test time, you're going to feel like, I got this. Like, I can do this. I know enough. I know what to do if I don't know. I know what I'm going to expect. I got this. That's the whole point of a Cram finale. So if you do not yet have your Cram finale pass, make sure to click the link below and get that pass. It's $15, which amounts to like $1 per review hour. So we're super excited to see y'all at the Cram finale starting Wednesday. But I'll stop there because we have this awesome Cram preview. Enjoy. I'll be around in the chats. Good luck to all of you. Chemistry, crammers, cram. All right, I'll stop. Okay, goodbye.
All right, what's up, everyone? So today we have our second preview of AP Chemistry, and we're going to talk about properties and calculations of equilibrium. And my name is Jahangir, just so you know. And in next nights, I'm going to be teaching Unit 7, but let's talk about equilibrium real quick. So we need to get a basic introduction for equilibrium, and we need to know reversible reactions, because usually in past units, we've had that straight arrow, but in reversible reactions, we have those double arrows going to the reactant side, going to the product side. So reversible reactions are chemical reactions that are going in both directions. And when we're in equilibrium, it's when the rate of the forward reaction is the same as the rate of the reverse reaction. So every time I think of equilibrium, I kind of think of it like a seesaw, but I have a pen. I don't have a seesaw right now. So I usually think of it like this. So we have our reactant side right here. We have our product side right here, and we're in equilibrium right now. But in equilibrium, we're in dynamic equilibrium, which means that the reactants and the products are continuously reacting. So it's basically like this. And when we have more products, look at that. The reactant side has to be favored in order to bring equilibrium back. And if we have more reactants, the product side has to be more favored. So it's basically a balancing act in equilibrium. And it's important to note that equilibrium does not mean the reaction has stopped, because in dynamic equilibria, we literally stated that the reactants and products are continuously reacting. So that's basically an introduction to equilibrium. And to show that on a graph, you might see these in many of your multiple choice questions or even some FRQ questions. It's when you have your graph and it's going to either the reactant side and the product side, and they're basically the same. They're parallel to each other. And that's when you know you've hit the equilibrium point. You've hit that bullseye. And next, let's talk about reaction quotient and the equilibrium constant. Now, equilibrium constant is usually denoted by the letter K, and this is a relative concentration of the reaction at equilibrium. So this is when we are at equilibrium. This is the constant that we're at equilibrium, and the reaction quotient is a relative concentration of a reaction species at any time. It doesn't have to be equilibrium necessarily. And to denote that for solutions like maybe water, it's usually denoted by C. So there's I believe it's a subscript, or I might be wrong, but it's like QC or KC, and you can see on the slides. And for gases, it's KP or QP. And this is on your formula sheet right here, where you have your equilibrium constant for solutions are shown and your equilibrium constant for gases are shown. So one of the greatest things you could use for your AP chemistry exam is your formula sheet, because it's given to you right there. Like if you forgot about your equilibrium constant, boom, right there, just in your formula sheet. And usually in equilibrium, we always want to compare the reaction quotient and the equilibrium constant to find out if the forward reaction is favored or the reverse reaction is favored. And if the equilibrium constant is bigger than the reaction quotient, the forward reaction is favored until equilibrium is reached. So it's basically like how the forward reaction is favored. So if we're having a little bit more reactants, our forward reaction is going to be favored, so we can balance that out. And if our reaction quotient equals our equilibrium constant, then we know that the system is at equilibrium. And the reverse reaction will be favored if the reaction quotient is bigger than the equilibrium constant. Now, to memorize this, I kind of think of it as the reaction quotient being on kind of the reactant side and the equilibrium constant being on the product side. Now, this is not true, but this is like something I try to memorize, and how if our reactants are bigger, then the reverse reaction is favored, and the products, the K is bigger, then the forward reaction is favored. And if we have too many reactants or too few products, the relative equilibrium, then we basically switch the sign. So that's basically the reaction quotient and equilibrium constant. Now let's talk about the magnitude of the equilibrium constant. And this chart, you should be very familiar with this in AP chemistry. So when our K value is like 0.001, it's like very small. The reaction barely proceeds. This is why we usually favor a higher K value, because a higher K value means that the reaction will be going to its completion. And reactants are a little bit favored when K is less than 1, but the products are favored when K is bigger than 1, when that equilibrium constant is bigger than 1. That's pretty much the magnitude of equilibrium constant, and that graph is that sort of bar graph that we showed in the slides. It's very important to know that. And now let's talk about the properties of equilibrium constant. And this is just, I kind of think of it as Hess's law, but it's with the equilibrium constant. So you know how in Hess's law, when you make it inverse, you change the sign of the enthalpy. Like if it's like positive enthalpy and you want to make the reaction inverse, you change the negative enthalpy. Well, with equilibrium constant, when you're changing the A from the reactant side and B from the product side, and you're switching that around, you want to turn it into 1 over K. So it's basically the inverse. It's 1 over equilibrium constant, and that's the inverse. And if you're multiplying the reaction by a factor, because I kind of think like Hess's law is a puzzle, but this is just like an idea from Hess's law. And if you multiply, then you basically have to put that as a subscript, or basically if you're multiplying by 2, you have to square it, multiplying by 3, cubing it, etc. And if you're combining two reactions, then you must multiply them. Unlike in enthalpy, you added them. For equilibrium constant, you want to multiply them. And that's basically the properties of equilibrium constant. Now let's go on to some practice for the equilibrium constant. And let's look at the question above. Consider the reaction of N2,3H2, and the product side is NH3, and we have a K value of 0.118, and we want to find the equilibrium constant for the reaction. So it's basically inverse. And as we talked about before, that inverse is just 1 over K. So when we convert that, we're just moving it inverse. So that'll be 1 over 0.118, and that would equal 8.47. Now, if this was an enthalpy question, if this was a sort of Hess's law question, then we would just change the sign. But this is equilibrium constant. So you want to memorize that. If it's equilibrium constant, it is 1 over K. And that pretty much concludes our practice for the equilibrium constant. And it's pretty simple. I usually think of it as solving a puzzle, and I've always loved puzzles. So it's just really fun to solve these questions. And don't get intimidated by these questions, because it's just, like I said, just solving a puzzle. And if you remember your rules for equilibrium constant, how it's 1 over K, and if you're multiplying it, then you have the subscript. If you're multiplying by a factor, you put in the subscript, and at the end you multiply them all together. That's the basics of practice on equilibrium constant. I'm going to move on to, I'm going to let Dylan take over.
All right. What is up, everyone? Before I get started, I just want to make sure, can everyone hear me, see me? Is that all working well? I've escaped the chat. I've made it. I'm a real boy now. Thank you so much, Jahangir. That was awesome. Such a great foundation for all the cool things we're going to be talking about with equilibrium. So the first thing we want to talk about is, how do we do math to actually calculate these equilibrium concentrations, right? Because we're given this equation. The first thing we want to do is plug some numbers into it and figure out what we're doing with it. So let's take a look at this problem, right? We have a fake reaction of A and B reacting to form AB, and AB splitting up in the reverse reaction to become its constituent A and B, right? So remember, both of these reactions are happening at once. Equilibrium occurs when the rates of these reactions are the same. I want to make it very clear that it does not mean the concentration of A and B is the same as the concentration of AB, but rather the rate at which AB is being created is equivalent to the rate at which it's splitting up, meaning the concentrations aren't changing. So let's take a look at these numbers, right? We're told that the initial concentrations of A and B is 2 molar, right? And then we're told that the equilibrium, so end concentration of AB is 1.15 molar, right? And of course, at the beginning, it's 0. We haven't created any. So to do calculations with an equilibrium constant, almost always you want to put together what's called an icebox. So an icebox is just kind of a mnemonic for remembering that what you need to remember is what is the initial concentration, how did the concentration change, and then what is the equilibrium concentration. So at first, we're given our initial concentrations, so 2 molar, and 0, because we haven't created any. And we know that we'll be creating 1.15 moles of AB. To find that change in A and B, we want to remember, for every 1 mole of AB created, that is 1 mole of A we lose and 1 mole of B we lose, meaning we lose 1.15 molar of A and 1.15 molar of B to create 1.15 molar of AB. If that doesn't make sense, feel free to ask a question, because I know that's a very shoddy explanation, but it'll make a bit more sense when we start kind of abstracting this out with X's in iceboxes. And of course, that means our equilibrium concentrations are, 2 minus 1.15 is 0.85, and 0 plus 1.15 is 1.15. Then we plug those numbers into the law of mass action, which is also known as the equilibrium constant equation. And that gives us okay. So I will repeat that quickly. So we are told that the equilibrium concentration of AB is 1.15, right? That's in the problem, meaning we know that throughout this reaction, when we reach equilibrium, we will have created 1.15 molar solution of AB, which means that the change column or change row for AB must be 1.15. However, to create that 1.15 molar solution of AB, we had to lose 1.15 moles per liter of A and B, because we had to actively form that, right? And the way those numbers change would be based off the stoichiometric coefficients, because we need to know is it 2 moles that are being lost, 3 moles, 4 moles? In this case, it's 1 and 1. So we lose 1.15 moles per liter of A and 1.15 moles per liter of B. And that is how we got that row for change. And then we take our final numbers, we plug it into the equilibrium equation, which I'll also probably call the law of mass action. They're the same thing. And we would get an equilibrium constant of 1.592. So let's take a second to try to just first understand, what does that number actually mean? What that tells us is that products are slightly more favored than reactants, which means when we reach equilibrium, when the rates at which we are creating and losing equalizes, right? At that rate, when that is equal, when that rate is equal, we will have slightly more products than we do reactants, right? The concentration will be slightly higher. And it tells us that the reaction goes slightly forward. Every reaction will go somewhat forward, but some just not, almost to the point where it doesn't happen. In this case, our equilibrium constant is quite high, actually. Okay, let's move on to another example, right? This one kind of turns the problem on its head. So, suppose the initial concentration of Cl2, oh, I see questions. So Isha says if it was 2A, there would be negative 2.30 for A's change. Yes, the problem is that kind of throws the whole problem into flux, mainly because then you need to balance the equation, so all of the numbers would change. But in general, yes, because now you're losing 2 moles of A for every mole of AB created. But remember that the numbers have to equalize if you're dealing with a balanced equation. So it'll make a little bit more sense, I think, after we go over this example here, right? So here we have a reaction of molecular chlorine reacting with molecular fluorine to form 2 moles of chlorine and fluorine, right? This isn't a reaction that'll ever happen, I don't think, but just for sake of example, right? Again, this was a reaction that will never happen. So we start off with an initial concentration of chlorine and fluorine of 4 molar, right? And we start with no chlorine and fluorine, right? So that is our initial, right? We're told that in the problem. And this time, we're not asked to find the equilibrium constant. We're asked to find the concentration of chlorine-fluorine, right? So in this case, we actually don't know what that change is because we don't know what the equilibrium concentrations are. So we'll call it X. We don't know, but we know we lose some chlorine, some fluorine, and create 2 times as much chlorine and fluorine, right? And we know that because of the stoichiometric coefficients, right? That's an important thing to note here. So now we know their equilibrium is 4 minus X, 4 minus X, and 2X, right? So those are our equilibrium concentrations. We can plug that into the law of mass action and just do the math from there. Now I see a couple of people here saying, is X negligible? I thought it was such a small change. Usually, yes. You're usually right in saying that. However, look at the equilibrium constant here. The equilibrium constant is 16, which tells us that reactants or products are very heavily favored, which means that X actually is very significant here. Right, so just like Charbella mentioned, it's not negligible here. Only when K is very, very small can you do that, because we assume that the change in X, like that change, is super small. There's a 5% rule where theoretically it's like when you have a 5% margin of error, but you usually don't have enough time to make that assumption. Typically, I like to say that if K is generally small, like 0.001 or lower, you can use that approximation, which we'll see in just a second. But in this case, you would have to use the quadratic equation to do so. So in this case, we can just do the math. In this case, I plug it into a calculator, and we're told that X is 2.667. Amazing. However, remember that we're not asked for X. We're asked for the concentration of chlorine fluorine, right? And that's not X, it's 2X. So we need to multiply X by 2 to find our concentration, which is 5.33. Also, actually, I'd do the opposite. No. So usually you're given an incredibly small equilibrium constant, like a very small one. I mean, typically, if you're given one that's like 16, we make the assumption that the reaction goes fully forwards. And we wouldn't be dealing with equilibrium here. However, what we want to know here is If it's very small, then we can assume that X is negligible. And Sophia, so yes and no. I mean, it's a quadratic, so you'll have to use some form of solving a quadratic, whether you choose to use the quadratic formula or completing the square or factoring, whatever. That's up to you and your math. But usually not so much. You can graph it. Yeah, like there are plenty of methods, but generally you'll be able to make the assumption that X is very small, and that means that you can make an approximation. And in fact, look at that. We're going to be dealing with X's and iceboxes right about now. So we might find when we do an icebox something like X squared over 4 minus X, right? That's not the exact thing we were looking at before, but pretty close. Let's say K is very, very small, something like 1.8 times 10 to the minus 5, right? Something tiny. Now we know that the products are not going to be favored in this reaction very much, and therefore that change in X, so if our initial concentration was 4 and we lost X, we know that that X is going to be really, 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 really small, right? So what we do is we can say, well, 4 minus X, that's roughly 4. Sorry, it says X on the slides. It should be 4. X is going to be super tiny, so 4 minus X is basically 4. For example, if X was 0.0001, 4 minus that is 3.9999. We can assume it's 4 and not make any sort of significant mathematical error. And it helps our math be significantly better, right? Because in this case, or easier and more manageable. Because in this case, we'd have to use a quadratic equation, but X squared over 4, we can just solve using square roots, which is super easy. So, wait, was there a slide? I think there might have been a slide deleted. It appears there was. Okay. Either way, the next thing we are going to be looking at is the way that equilibrium responds to external forces, right? So let's say we have a reaction at equilibrium, right? Whatever that reaction is relevant here, but we have some reaction. What happens if we add something to this, right? We increase the concentration of one of the species, decreases the concentration of one of the species, put it under pressure, increase the temperature. Any of these external stimuli will change the equilibrium concentrations. And that's what's known as Le Chatelier's principle, right? So Le Chatelier's principle tells us that a system will counteract changes to equilibrium. So, for example, right, let's think about this like a seesaw, like we were talking about earlier, right? Let's say our reaction is at equilibrium, right? Our reaction is at equilibrium, and now suddenly, let's say this is reactants and this is products. We had a bunch of products. Oh man, we're lopsided now. We're no longer at equilibrium, right? What we want to do to equalize this is bring this side down. So decrease the amount of reactants, or excuse me, increase the amount of reactants, right, to equalize this out, right, and bring it back. So that's how a reaction actually responds to changes in concentration. So for example, in this case, right, we have A plus 2B yielding C plus D, and then the reverse reaction. If we increase the concentration of A, right, suddenly we have an excess of A, and so to return to equilibrium, that forward reaction is going to take place, increasing the concentration of C and D, right, so on and so forth. This is actually just a consequence of us changing Q, right? Remember, Q tells us at any given point where we are relative to equilibrium. So if we throw a bunch of A into this solution, what we're actually doing is taking Q and decreasing it, right? Because of if you increase the denominator, the number becomes smaller. And so Q is becoming smaller until it's eventually less than K. And when Q is less than K, you need to create more product to return to equilibrium. That's all that's happening. So that's the most common form of Le Chatelier's principle, is typically changes in concentration affecting equilibrium. The next way that we see Le Chatelier's principle impacting things is in changes in temperature. So there was a question about this earlier, actually, and I will throw it up. Let me see, where is it? It was just here. There we go. Right, so someone asked, how is K related to temperature? Right, I'm not realizing that's actually not what they were asking. But we can actually talk about how temperature impacts the position of equilibrium, right? If a reaction is exothermic or endothermic, we can think of this as heat being a product or reactant of that reaction, right? So let's say, for example, heat is a product, right? We have an exothermic reaction. If we increase the temperature, we can think of this as adding heat to a system, and therefore, like concentrations, for an exothermic reaction, if we add heat, we will force the backwards reaction to occur, and vice versa. And that's simply, again, because if a reaction is favored to produce heat, increasing the temperature will force it to go backwards to manage out that concentration, or to manage out that equilibrium. Okay, so similarly, we have an increase in pressure, right? This is specifically for gas-based reactions, so you won't see this in like a reaction in solution. But for a gas-based reaction, an increase in pressure can actually change the position of equilibrium. So an increase in pressure will lead to a shift with the side of fewer moles of gas, primarily because if you think of partial pressures, like concentrations here, right? If you increase pressure, you'll need to manage the ratio of partial pressures, which means you will need to go to the side with fewer moles of gas to balance out those partial pressures. And if you remember Dalton's law of partial pressures from Unit 3, partial pressure is directly proportional to moles. So that is why it connects to the side with fewer moles of gas. All right, so if you have any questions about that, feel free to ask any questions. We have tons of people in the chat. And that is definitely, Le Chatelier's principle is actually, I think, a fairly intuitive way of thinking about equilibrium, right? It's thinking about equilibrium not as a stable process, but as a dynamic process that is constantly occurring. So when you throw a stimulus on there, it has to actually react to return to equilibrium, right? So, for example, if we, in this reaction right here, the A plus 2B yields C plus D and vice versa, if we throw a bunch of D into this, right, we increase the concentration of D, we suddenly need to account for this by increasing A and 2B in order to return to equilibrium. So the backwards reaction is going to be favored. Similarly, let's assume this reaction is endothermic, which means heat is a reactant. In this case, heat is a reactant. So if we decrease the temperature, let's say, for example, now suddenly, can I repeat the first part again for changing the Q? Sure. Yeah, absolutely. So with concentrations, right? Remember that Q tells us where at any point in time a reaction is relative to equilibrium. So if Q is less than K, the reaction needs to keep going. We haven't reached K yet. If Q is greater than K, we've overshot equilibrium. We need to go backwards. And if Q is equal to K, we are at equilibrium. So looking at Le Chatelier's principle as a change of Q, if we increase the concentration of A, right, that will decrease Q to the point where it will eventually be less than K, which will force the forward reaction to take place, which is exactly what Le Chatelier's principle tells us it will. A system will counteract changes to return to equilibrium. So that is the general process. This is just a quick question. How would we figure out, given a reaction, whether it is endothermic or exothermic? There are a number of ways. Typically, the way you do this is look at the enthalpy value, and that will tell you exactly whether or not it releases heat or takes in heat. And that's typically how you'll know in the exam. All right. So it is time for a quiz. So what we're going to do next is we are going to move into a quiz created by Elias, one of our Cram hosts, and we are going to see how you guys do. So let me pull up the quiz really quickly. Can everyone see it? I'm going to assume it's good. And I'm going to pass it on to Anuva to run the rest of the quiz.
Okay, so I believe you just have to click the link and then we can start the quiz. It's going to be like a Kahoot style. Just to introduce myself, I'm Anuva Yanzan and I am a senior in New Jersey. I'm also taking AP Chem and I'll be your Unit 5 specialist on night 1. So if we want to start the quiz, maybe. Okay, there we go. So I'm sure you guys can see it on your screen, but I'm going to read it out loud. Just the question. A reaction vessel is filled such that the concentration of hydrogen gas, chlorine gas, and hydrogen chloride each have a partial pressure of 1 atmospheric pressure. What happens to the total pressure of the reaction vessel as the reaction proceeds to equilibrium? So I'm assuming we can just wait maybe like a minute or two, and then we can just wait for everyone to come in, and then we could also reveal the answer and discuss about the answer. Let's wait until the number gets a little bit higher, but if you guys want to like drop in the chat if you have any other questions about equilibrium, and then in between these questions, I could try to help answer those questions, and then other people in the chat could also answer. And we could just reveal it when it gets to like 60. Cool. So the answer is D. The total pressure will remain constant because the forward and reverse reaction are at equal rates. So basically, this is just the definition of equilibrium when the forward and the reverse reaction are balanced, and like the products and the reactants, like the, what do you call it? Like the reaction rates both ways are constant. So basically this applies to whether you're doing like total pressure, or you're doing even like whether it's like a gas or like a liquid. For example, if you're mixing two liquids and like you're finding the equilibrium of that, this concept of equilibrium will apply to virtually any reaction. So if we could move on to the next question. What is the purpose of calculating the reaction quotient Q in a chemical reaction? So we'll just wait until it gets to 60 people answered, and then we can reveal the answer again. So these quiz questions, so I believe most of these are theoretical, which can appear on the AP exam. But they're more testing like the concept rather than like the actual like AP exam question. Because in the AP exam, you're going to see a lot of like more multiple choice that will try to incorporate multiple units. But just like Dylan just said in the chat, they might be connected to questions that you might be asked on the AP exam. Dylan, if you want to reveal the answer. Yay. Okay, so C, it's to predict the direction of the reaction at a given moment in time. So just remember, I believe Jahangir went over this, but Q equals K at specifically equilibrium. And Q will like definitely be changing because Q equals the concentration of products over the concentration of reactants. So when you're calculating Q, you want to find like the you find the direction based on like whether there's more products or there's more reactants within the chemical reaction. So yeah, if we want to move on. So 3, which of the following statements is true regarding the relationship between the reaction quotient Q and the equilibrium constant K? So I briefly went over this, so I hope you were listening, but yeah. I think Dylan's copying it in chat, yeah. You can either use that or you can use the QR code. You guys should definitely drop in the chat on a scale of 1 to 10 how you guys are feeling about Unit 7 equilibrium. I know we haven't like covered the entirety of equilibrium, but definitely drop like how you're feeling after today's preview and how you're feeling about this quiz. Okay, we can reveal the answer. Okay, so see, I know this was a little bit tricky, but just remember, so like if you compare like K as like a constant value, it's literally called the equilibrium constant, and then Q the reaction quotient. So then if Q is bigger than K, that means if Q is bigger than K, oh yeah, I just realized it was reversed. Yeah, if Q, if Q is bigger than K, then there is, okay, yeah. If Q is bigger than K, there's more products over the reactants. So then it would want to go in the reverse direction. And then, so literally the opposite of B and D. And then if it's smaller than K, then there would be more reactants than products. So then it would want to go in the forward direction. So then it makes more products. But A is correct, where if Q equals K, then the reaction is at equilibrium. But definitely exam tip, read all of your answer choices, because while B and D might look correct, it's quite like the opposite. So yeah, if anyone has, yeah, I know it's supposed to be A, but yeah. Okay, so for the reaction below, what's the equilibrium constant expression for NH3 plus 5O2, and then the double-headed arrow for NO plus 6H2O. Yeah, so when your Q is bigger than K, I believe it's because Q equals the concentration of the products or the concentration of reactants. It will want to go in the reverse to make more reactants because of the imbalance. And then when Q is less than K, that means that there's more reactants than there is products. So then it will want to proceed in the forward direction. So it makes more products to balance out that ratio, because essentially it wants to get to a ratio of 1 where the products are equal to the reactants. Okay, so I think we can reveal the answer. Oh my gosh, 100 guys. So we got it. A, which is NO4, concentration of NO4, well, NO to the power of 4, and then times the concentration of H2O to the power of 6 divided by the concentration of NH3 to the power of 4 times the concentration of O2 to the power of 5. Congrats, guys, you got a 100. But just to make sure, just remember like the coefficient of like how many moles of, for example, NH3, it becomes the exponent when you're putting it into the equilibrium constant, and then it's products over reactants. Okay, nice job, guys. So which factor does not impact equilibrium? Definitely a very cool tip by Alana. I hope I said that right. But yeah, just like Dylan said, you want to make sure you understand the math just in case, like, for example, you get something like computational and like an FRQ. But definitely it's something like quick to remember it by, which is really smart. Okay, so we can reveal the answer. What does that even say? I can't even read it. It's such a big number. But majority of you guys, we're getting this 5. So it's saying which factor does not impact equilibrium. So the factors that do impact equilibrium, which is pressure, concentration, and temperature. The only one out of these is catalyst, and it's because the catalyst speeds up to forward the reaction or like for the reverse reaction to an extent. And then like when you add a catalyst, it doesn't affect like the relative rates of the two reactions. And it also like doesn't affect like the position of equilibrium. It just makes it faster to get to that point. Okay, cool. So if pressure is increased, which way does equilibrium shift? Yeah, congrats on that last question, guys. I can see the 5, I'm manifesting it. Yeah, definitely manifesting that 5. Okay, we can probably reveal it soon. The exam is curved. Don't worry, guys. You don't have to get like a 100 in order to get a 5. Okay, so the answer is A, to the side with fewer molecules of gas. So remember Le Chatelier's principle where it's like if you increase pressure, then volume decreases. So volume in this case is the moles of gas. So yeah, and then like it doesn't matter which way of like the reactant or the product side, it matters what the volume is because again, if we're increasing the pressure, then we are decreasing the volume in order to keep Le Chatelier's principle. I'm also a Le Chat kind of girly. Okay. If K equals concentration of B over concentration of A for the reaction A equals B, or the double-headed arrow, what will K be for the reaction 3A equals 3B? Definitely manifesting that A on your final tomorrow. I have my chem final on Friday, so yeah. Yeah, I believe it's like there's like certain cutoffs. I don't think it's necessarily a curve, but Dillard's right about like there's like different cutoffs for 3, 4, and 5, depending on how hard the exam is. So yeah. I'm not sure when they decide curves when they're grading, but it ends up working in most people's favor, I think. Okay, so we can reveal the answer. Okay, nice job, guys. That's a 94. Where it's A, K equals a concentration of B to the power of 3 over concentration of A to the power of 3. And just to repeat what I said earlier, it's K equals products over reactants. And then when you're using that coefficient, so like for the 3A and the 3B, just remember to put that coefficient as the exponent, because it's technically that coefficient's the number of moles. So yeah. Okay. So consider the reaction N2 plus 3H2 equals 2NH. It's like a little bit blurry, but that has a K equals 0.118. Find the equilibrium constant for the reaction 2NH3 plus equals N2 plus 3H3. Yeah. Sorry, I'm like seeing it on the little screen that you guys are and reading that off. But you guys can see it on your own screens. Oh yeah, they're allowing calculators on the Chem MCQ this year. Little bit, I think it's gonna add more calculations within the multiple choice, but I think it'll be okay. I always hope there isn't much on acids and bases, but we got you. If you guys don't really understand acids and bases, make sure you come to night 2. I believe Dylan's teaching it. But yeah, I think like inclusion of the calculator, it's probably going to be more like computational stuff. But like not to like a great degree, like for example, the HH, they probably just give you a bunch of numbers and then have you do that. Okay, maybe we can reveal the answer and then I can talk about how to do it. Oh, wow, okay. So the answer is C. And basically how you do it, if you notice like for the 2 different reactions, like so for the K value of the first one, it's literally the reverse. So you're taking 2NH3 equals N2 plus 3H2, which is like the reverse of the first reaction. So since the reaction is switched, you take the inverse of the K. So 1 over 0.118 is C, 8.47. So yeah. It's okay. I had to get a refresher on that one too. It's all right, guys. In a particulate diagram, which key principle is being used to determine the distribution of molecules? So to answer them, you have to either scan the QR code or then, yeah, copy the link that Dylan just posted in the chat. And you can join us in the quiz, and it's like Kahoot style. So then you answer them, and then we reveal the answer and see how many percentage of people chose the right answer. I do think particulate diagrams are used on the AP exam, probably for more like conceptual things rather than you having to like count out like each molecule within the within like a beaker, for example. But yeah, we can reveal the answer now. Okay, nice job. So it's the law of conservation of mass. So if you take like a picture of a particulate diagram, you're going to see like for example, like in a beaker, you'll see like how it goes from like, for example, like one set of reactions with the reactants, and then it goes to like the products, and then you can see like how the different molecules react with one another, and how, for example, like hydrogens and like chlorine both react. And while you still see that like they're reacting, you'll see that like each of the individual atoms are still there. Like you don't lose any atoms, you don't gain any more atoms. So yeah. If anyone needs me to re-say that or I guess explain it differently, let me know in the chat. But yeah, I think we can move on. Literally, if you like look up a particulate diagram, you'll know exactly what I mean. I'm sure you guys have seen it at least once in AP Chem. So yeah. Okay, so consider a particle diagram of the equation 2x plus y equals x2y. If there are 10 molecules of x at time t equals 0 and 14 molecules of x at time t equals 10 seconds, which way is the reaction shifting? Okay. Dylan, would you be able to pull up a picture of a particulate diagram? I don't know if you can do that. Okay.
I will after this question though, just so that people
Okay.
can read it and answer.
Okay.
But I'll have it
So
pulled up.
we'll answer this question and then we can go look at it. Yeah, particulate diagram. I honestly had no idea what a particulate diagram was until like I looked up a picture of it and I was like, oh yeah, I definitely know what that is.
You've definitely seen one. If you've gotten through AP Chem without seeing a particulate diagram, I'd be surprised.
I think
but
particulate diagram is just a fancy way of saying like the diagram.
It's a fancy way of saying the funny pictures with dots as atoms. And
Yeah.
Noah, to answer your question, not by maybe you might have to. I've seen exams where you have to, but you'll never be like judged on your artistic ability. As long as it's clear what your answer is, you'll be fine. And once you see what a particulate diagram is, you'll be like, okay, I can draw that.
Yeah. Okay, so I think we can reveal the answer. Okay, nice job. 74. So the reaction has shifted to the left. So remember the left is towards the reactants because we have first 10 molecules of X at the beginning of the reaction. And then since they're gaining molecules because 14 is more than 10, molecules of X, you'll know that there's a shift to the reactants because X is on the left side of the equation, which is the reactant side of the equation. Okay. So Dylan, do you want to pull up the particulate diagram?
Yep. There we go. Yeah, so that's a particulate diagram. Quite literally, for this instance, it's of a precipitation reaction between silver nitrate and sodium chloride, producing sodium nitrate and silver chloride. But it's just, yeah, like the picture of the reaction taking place.
Yeah, so if you like see like for the law of conservation of mass, like mass cannot, exactly what Jahangir just said, mass cannot be created nor destroyed. And with that, like you can see that like while they are reacting, all of like the individual atoms are still there. So like if you like count them all out and like count how many like sodium, chlorine, like all of that, you'll still have the exact same on both the reactants and the product side.
I'll also note this is also showing, it shows the conservation of mass, especially because you can see we have an excess reactant in this reaction of chloride ions. And so because mass cannot be destroyed, we still have that chloride in excess, and that's displayed in the particulate diagram.
Mm-hmm. Yeah, my teacher is giving a final literally on Friday, which is like the last class day that I have before the AP exam on Monday. So I hope that answers your question, Emma. But yeah, if you guys could go check out our poll and fill it out, then that would be great. So if anyone else has any questions, I know it's 2 minutes until 9 EST. So yeah. Yeah, I'm having my final and this is I believe the law of conservation of energy is wrong just because that's not specifically what a particulate diagram is meant to show. I believe the question is like, what is a particulate diagram displaying? And especially when you look at a particulate diagram, it's like evident you see the law of conservation of mass. Any method I'd recommend to do for practice problems for the exam. So online, there's like a ton of resources. I know College Board posts like FRQs. Every single year they release the FRQs from the previous year. And yeah, you can do those. I know College Board has released multiple choice as well, where you could see those. Print off worksheets. I know for if you're joining us for our crams, we're going to have study guides that you could also take. And yeah, I mean, like worksheets, honestly, you could just look up anything. I know if you want to look at like Fiveable's AP Chem section, it's pretty helpful. I find it helpful, at least. Dylan, did you want to pull up number 1 again so we could explain it? Just one last time.
Yeah, I got it. There it is. Oh, it looks like it went away. But the question is there, and the answer in this case is C.
Okay, yeah. So again, just like if you look at the definition of equilibrium, it's like when the forward reaction and the reverse reaction are the exact same. So then when you're doing like any reaction, whether it's not even just gas, it's like with liquid or like basically any reaction, for equilibrium, for this case specifically, the total pressure will remain constant because there's equal quantities of the reactants and products. So I hope that answers it, because the forward and the reverse reactions are exactly the same. So the pressure will remain constant because you're not like adding more pressure. So yeah.
All right. It is time to wrap things up, unfortunately. Huge shout out to the Chem team. Another awesome Cram preview. And if you guys want more AP Chem review, be sure to join us this Wednesday for our Cram finale first night. It's going to be awesome. 3 hours starting at 7 o'clock EST, taking us to 10 o'clock. 5 nights leading up before the exam. We're going to be covering everything. It's going to be such a good time. If I could get one of the hosts, just drop that link for the Cram passes in the chat. Audience, thank you guys so much for joining us. The chat was awesome tonight. I hope that we feel a little bit better about equilibriums, and I'm super excited to see you guys on Wednesday for the starter Cram finales. So take care, guys. Have a great rest of your night, and I will catch y'all later.